Hey, Cece. Hope you're having fun. So here we are. We're going to start the angled projectile notes. We just finished going over the homework, so all of your classmates have that. Okay, so the difference with this type of motion, here's what we had before, right? We started off horizontally, and then it dropped down like that. The type of motion we're talking about now, we're going to start with an initial angle. So we might have, right, something like this. So think about when you shoot a basketball, right? Or you hit a golf club, right? Or ball. I guess you hit the golf ball with the golf club, right? Okay, so it's going to go up and over. So when we start the motion, right, there's going to be an angle involved. Okay. Now it could be a complete parabola, kind of like I've drawn here, like a golf ball sailing through the air and then hitting the ground. Okay. It could be like a basketball, which maybe doesn't complete that parabola. Maybe it's just something like this much of it, right? But it's always starting with some angle, okay? So we're gonna have to include the angle when we start working our calculations. So the equations really aren't changing. They're gonna look different, but all we're gonna be doing is including the angle, okay? Now, when we start, I'm gonna draw it really big. Oops, here we go. Okay, so let's say that's the beginning of it. So if we kind of imagine the beginning here as sort of a triangle, right? If this is our initial velocity here, right? It is at an angle, and that initial velocity does have an x component and a y component. So if we're using an equation that includes initial velocity, that's also a horizontal equation, rather than using this initial velocity they gave us, oops, we just want to use the x portion of that velocity. Okay. Or if we're working an equation that's looking at the vertical part of the motion, we would just want to use the vertical part of that initial velocity. And the equations are actually really nice because you don't have to first resolve it and then plug that number in. You can just choose the equation that will have the resolving in it for you. This, if we look at V, yes?
So can you give an example of when you're talking about, like, use it to find horizontal?
Okay, sure. So let's say this is kind of our picture. We're shooting a basketball, and we want to know how high does the basketball get? We'd be solving for a delta y. That would be a vertical component. So if we choose the equation, delta y equals vi delta t plus 1/2 a delta t squared, that initial velocity in the equation would have to just be the y part of the initial velocity. Okay? And it's really easy. What the equations will do for you is show you that, well, the y part of this velocity, if we were kind of writing out in trig form, this would be the same thing as the vi times sine of our angle, right? And this one down here is the same thing as vi times cosine of our angle. So we're never going to write just vi. We're going to either write vi sine theta for the y part of the initial velocity, or we're going to write vi cosine theta for the x part of the initial velocity. Does that make sense? Okay, so let's take a look at the equations. And once you understand the whole vi sine theta, vi cosine theta, the equations, I think, make a lot of sense then. Okay? So we have delta x equals vi cosine theta delta t. So instead of saying vx or vi, we're saying vi cosine theta. Okay? And that's our horizontal equation. The green one, of course, shows you what we used in the last section in the previous chapter. It's the same equation, it's just that our Vx is Vi cosine theta, okay? So I'm just kind of showing you like what we just talked about. So if you were thinking in terms of what's the x part of the initial velocity, what's the y part of the initial velocity, that's why we're using Vi cosine theta or Vi sine theta. Okay, so here's the equation that I just mentioned to you when I was giving the example of how high the basketball is. This was our equation in the last section, right? Delta y equals 1/2 ay delta t squared. We used that because there was no initial velocity in the y direction. Now we do have an initial velocity in the y direction, but rather than just saying vi delta t, we have to say VI sine theta delta t, because VI is on an angle, right, and A is vertical. So we want to make sure we're only using the vertical part of that motion.
You said no initial velocity in horizontal?
For the green one. That's why we used that last time. We kind of dropped off the VI part because we didn't have an initial velocity in the Y direction, but now we do. Okay, and then this one, our last one, is it our last one? No, there's one more, second to last one. So we were using VYF equals acceleration times time, which we used when we were explaining our homework question. Originally it was VF equals VI plus A delta T. So again, we can't just say VI because VI is on an angle, and acceleration and our velocity over here are vertical. So we're just going to use the Y part, so VI sine theta in place of just VI. Jessica? Because they're really all the same, I mean, these are all the same formulas. They're just slightly tweaked to make it easier, what you're doing, exactly.
So will the Y always be sine and the X always be cosine?
In these, yes, because it would be really, it would be awkward to like have a different orientation for that. I mean, I don't know how to imagine that. I guess if you were
looking down.
Yeah, if you were looking down or something, but I don't think I've thought of a way to do it so that it wouldn't be sine is with the Y and cosine is with the X.
Okay.
So, right, in our last equation then, this is our squared equation, so VYF squared equals VI squared sine theta squared. That's 2A Y delta Y. And so it's the same, we still have the same really 4 formulas that we've been using all along. The delta X one, the delta Y, and then the 2 VF ones. They just look a little different to incorporate our angle, okay? So let's do a problem. That's all the notes for today, but let's do a problem. Oops. All right, so let's go to OneNote. And let's grab a new page. I don't think I had, okay. Okay. Okay, a baseball was thrown at an angle of 25 degrees relative to the ground with a speed of 23 meters per second. If the ball was caught 42 meters from the thrower,
What's the O next to 25?
it's supposed to be the degree, I just have to raise it up still. How long was it in the air? How long was it in the air? And I think there's another part of the question. How high above the thrower? Okay. How high did the ball get? Okay. So before we kind of jump into this, I want to think for a minute about what kind of information we can assume. I'm going to make this a little bit bigger because it seems kind of small. Because there is information that we can assume, which will make the problem solving easier. So if we think back to the first chapter when we were doing, when you throw a ball up in the air, what do we know about the highest point the object gets in the air? Its velocity is 0. The same thing is true for motion like this, okay? We can still assume that at the very highest point, that velocity is 0 meters per second, okay? Now we can use that to our advantage. We know the ball's not gonna stop there at that point, right? But we could kind of just look at this much of the motion and say, right, if we say, oh, I'm just gonna look at this much of the motion, then that velocity we could call our final velocity, okay?
Make it good together.
Exactly. All right, so let's see what we have in this problem. I don't know why I can't erase. You can't erase, like the eraser's there.
Oh, it's racing.
It's really slow. Oh my goodness, are you serious?
Yeah, it's about to ring in a minute.
Okay, so we're gonna stop here. I'm not gonna give you the homework sheet because I don't know that it's, I mean, it's up to you guys. You wanna give it a try first and see, or?
I don't even know how it starts.
All right, so we'll hold off here, and then Monday we'll go over the problem. So actually, Cece, you lucked out. All you missed was the presentation.